Out of the recitation notes, so there are many of you in here who are not registered, which is fine, that's okay. But let it be the lessons in the rest of you that you can show up early. In the future, we'll try to have more for you guys. For those of you who are not registered, that's fine. What I would encourage you to do is to go ahead and check again next week. I think both 202 and 203 are over enrolled at this point, but I asked them to open up some more spots in registration, so they might be able to let you register next week, so just double check again. I think registration, they bumped it forward because of the snow days. It should end around like Thursday or Friday next week, so just double check again next week to see if you can officially come to this section. It just makes things a little logistically easier. But again, even if you can't, you're still welcome to come. A couple other pieces of general information. First thing, staple your problem set when you turn it in Monday or Tuesday. We're not going to grade it if you don't staple it, so it's an easy way to advance yourself in life. Second thing is we're grading the problem sets primarily on effort. So there's a couple parts in the problem set, I think particularly like later parts of problem 2 that are quite challenging. Just go ahead and take a shot at it. If you take a shot at it, we have seats up here in the front. Yeah, actually we have a seat right over here. So if you guys go ahead and just take a shot at it, we'll probably give you credit. You definitely need to tackle the easier parts of the problem set. If you don't do the easier parts, we're not going to give you credit. And then great, and then if you guys have questions, my probability of responding to your questions by email decreases rapidly over the weekend. So if you have any questions, I would strongly encourage you to get them to me today. My email is andywwu@wharton.upenn.edu. And if I can give you one piece of important life advice right now, your email address actually works without the Wharton part. I find a lot of people don't know this. My email also works at andywwu@upenn.edu, and this works for you guys as well. Alright, good. So let's go ahead into the content for today. There's 3 things we're talking about. We're going to do it a little out of order that's in the notes here, so we're going to jump around a little bit. The first thing that's in the packet, but we'll talk about last, is the electric vehicle example. So that's demand aggregation of electric vehicles. So that's number 1. Number 2 is going to be looking at MRS, so marginal rate of substitution and how we apply that. Number 3 is going to be doing a utility maximization problem with a kinked budget constraint. So, demand aggregation of electric vehicles, marginal rate of substitution, and utility maximization with a kinked budget constraint. So we're going to go a little bit out of order in the packet here today. So you're going to want to start, kind of flip to page 4. So start on page 4. We're going to talk about the MRS first, because this is really relevant to your homework. So remember that the price ratio, and we talked about this in the first recitation, the price ratio is the slope of the budget. Is the slope of the budget. We abbreviate BC, which you guys should have seen many times already. So what's the definition of this? The slightly longer version is the rate at which the market allows you to trade off a unit of X for Y. So the key word in this definition here is the word market. So this exists outside of an individual consumer. This is the whole market. So again, sort of refresh what that looks like. Budget constraint. It's this slope of that line.
And what's the market again?
Sorry, what?
The market is the consumer.
No, it's different than the consumer. We'll talk about the consumer in just a second. Yeah, it'll make more sense when we combine them. we talked about both of them. So next we're going to move on to the MRS. To the MRS, is the rate. You would give up 1 unit of X. For an extra unit of Y. While maintaining the same utility. So this is a function of your preferences. And you can also think of it as the slope of the emissions curve at a single point. All right, so just to, again, intuitively emphasize what the difference between these two things is, the first thing here is the slope, relative to the market. So we're only thinking about the market, and what does the market have? The market has prices, right? So this only takes prices into consideration. The MRS is a parallel, but only for consumers. So it's going to essentially take the trade-off, but for a consumer level. So let's go ahead and derive the MRS. So I'm going to fix utility at a certain point. And then we're going to totally differentiate. And then rearranging. So I'm going to go ahead and draw a graph that you guys have probably seen already. So we have goods X and Y. I'm going to go ahead and take this budget constraint that you guys already know. I'm going to draw that here. And then I'm going to draw a single indifference curve. Keep in mind that indifference curves are a mapping, so there's a whole bunch of indifference curves. But for all intents and purposes for this class, there's only one that matters. It's the one curve that's going to end up here. So this is the point of tangency. This is what we call the optimal bundle. So essentially everything that's going to happen in the first part of this class is essentially how to find this point. So you're going to see lots of different problems, lots of different variations where the budget constraint contains the utility function looks really weird. In your homework you'll have a budget constraint that looks like this. Like literally a straight line. Sorry, an angular line. That's the min function. That's going to be a different kind of utility function. Every single part of this first part of the class is different variations of this problem. That's all you're doing over and over and over. So you don't need to freak out. When you see this on an exam, you're basically dealing with this. How do we solve these problems? Essentially what we're going to do is we're going to set MRS equal to the price ratio. Yeah, you can just keep writing this on page 4. I don't think there's another space. So MRS again. Let me just recopy that. And then price ratio is going to look something like this from your prior lectures. So generally it's going to take that form. Before you write too much though, I would encourage you, and this is the way I like to think about it, you can go ahead and just drop these negative signs. You do not need these negative signs. The reason the negative signs are there is because this is negatively sloping, but in practice it doesn't matter. Just set them equal. The trick to remembering this function is that the x's are on the same side and the y's are on the same side of the division sign. You could write the whole other way. It's the same thing. All right, so we're going to go ahead and do a problem. So we're going to move on to the next page, page 5. And I'm going to do a problem with a kink budget constraint to show you how you might use this. So you guys have any questions? Go ahead.
Can you explain how you derive MRS? Like, can you just walk through your thought process? Just like that. I just don't know what
I don't have, there's no good explanation. It's just literally if you go into your calculus textbook and look at the definition of total differentiation. Yeah. So essentially it's the general idea is that for a given change in the utility curve relative to x, dx, keep in mind that means like a literal, like the actual amount of change times that amount of change. Plus if the change in utility relative to y times an actual amount of change in y, that together will be 0. So if you go, it's basically the definition of total differentiation in both of your calculus textbook. They'll probably have a better explanation than I will here.
How did you get to like from du dx to
Sorry, mu is just the notation we use. Mu we mean like this. Yeah, so it's just a definition, we made it up. Alright, so we're going to move on to the next example. So kink budget constraint. BC budget constraint. Alright, so we have the following problem as written out there. So utility M1 half, A1 half, and then budget constraint given that information below. So we've got to write out the consumer's maximization problem. It's going to look like this. And make sure when you're solving these kind of problems, make sure you always go ahead and just write this information out. Make sure you always write out the full budget constraint. Keep in mind these two letters here. Go ahead and write them out so you know what you're going to be solving for. All right, so let's go ahead and find the consumer's MRS. So let me just go ahead and write it out. Actually, sorry, for those of you who don't have worksheets, are you sitting next to someone who does? Can you guys see somebody's worksheet? Okay, you okay? All right. All right, so what is the marginal rate of substitution? All right, so we're going to go ahead and keep going here. Keep in mind, we talked about how there's a negative sign. I'm going to go ahead and just ignore the negative sign. Just bear with me. It actually doesn't matter. So what's the derivative of this with respect to m? And then what's the derivative of this with respect to a? And that's the MRS. In order to find, actually let's go ahead and simplify this a bit more. So the 1/2s cancel out, move this up, move that down. It's going to be A over M. Good. So to find the super's demand function, let's go ahead and make some space over here. So MRS equals price ratio. So that's just the function as we've given. Keep in mind that the m's are on top, the a's are on bottom, it's the other way around. I'm going to copy what we have, which is A over M. So A over M is the left-hand side. The right-hand side is as is. And then if we simplify this again, we're going to have and then we're going to take this and plug it back into the budget constraint. So I'm just going to recopy the budget constraint here. I'm just going to go ahead, let's start with, I guess, M. So put that, put that over here. And that's going to simplify out too. So we found M. And then we're going to find A. I'm not going to do the math here, but you can sort of guess that by symmetry it's going to equal the following. All right, so let's just intuitively look at our answers here. So we found that M is a function of I and PM. So it's a function of the price of the product itself and the income. Notice that the amount of M that we're going to want is going to increase when the income goes up. It's going to decrease when the price goes up because it's inversely related to the quantity. Similarly with A. So this answer intuitively checks out. So this is probably correct.
Is that for all cases?
That should be a function of.
Like inverse relation?
Not necessarily. So you can imagine, we could design a problem where the when the price increases, you demand more of it. So for example, let's say like Beats headphones, I think because it costs a lot of money, people may want it more. So you can design a problem like that. In general, it'll end up like this because this is what we believe in neoclassical economics. So we have those assumptions. We have price equals 1, A equals 1, and I equals 30. We're going to find the optimal allocation. I'm actually not going to actually just do it right now. Oh, this is also being equal 15. All right, moving on to the next page. Wow, we typed that incorrectly. So muffin means make your toy. All right, so next page, page 6. So we are on page 6, and then we're going to look at, so suppose the store is running a promotion where the first 12 bottles cost PM equals 1, and the price drops to 0.5 for each additional unit. So there's a very similar problem in the problem set to this. So this creates a kink in the budget constraint. So what's the cost function of M? Well, the cost is going to be nonlinear. We're going to have the following function. So let's go ahead and intuitively think through this. So by cost, we mean sort of the total quantity times the price. So the component of your budget that's going to come from M. So when M is less than 12, or less than equal to 12, it's exactly as we had before. So total component of price from the M is going to be price times M, simply. When we get above 12, that's when it gets confusing. And let's intuitively work through how this is going to work. So when you are M greater than 12, by definition, you must have consumed the first 12 bottles, right? So this part is a fixed component. This is actually a constant because P is a constant, right? Because we've assumed that we're greater than 12 for the sake of this argument. For every amount greater than 12, so say we consume 13, so there would be one more than 12. 13 times minus 12 is 1. Times the new price, the lower price. Now contribute this component here. Does anyone have any questions about how we do that? All right, so then the budget constraint is going to look a little bit like this. So under the promotion, the budget constraint is going to look like the following. So we're taking a budget constraint anywhere. The original budget constraint, as we wrote it out, looks like this. We just plugged in 1, 1, and 30 into the original budget constraint from the start of the problem. We just took the real numbers. And then for this component here, what we did was we took this piece here, just put in real numbers, and then PM here is 1, PM prime 0.5, put that in here, brought out this component here, which is 1, and then I equals 30. Sorry, go ahead.
For the second equation, is that 1 times 12?
That is right, that's 1 minus 12. So I guess for a little more clarification, we can also write it like this. See where everything's coming from.
And the ones are all the original prices.
That's right. Yeah, we're simply just plugging in the prices. There's not much going on here. So do you guys have the sign-in sheet in the back?
Yeah.
Hey, can you bring that up here?
Yeah.
There's 2 back there, actually. You should have them signed. All right, so we've got our budget constraint, right? And now we see how the consumers optimal allocation is going to change based on this promotion. So we have a budget constraint with a kink in it, and then there's going to be two optimal slopes or price ratios depending on what part of the budget constraint we're looking at. So I'm going to go ahead and jump some steps here. Thank you. So the first thing is I want to go ahead and consider the range between (0 and 12). So between 0 and 12, we've got the following budget constraint as listed right here. This budget constraint. That's the same budget constraint we were working with before. Under this budget constraint, we actually solved the problem already. We solved the problem this way. We found that we found that, right? That's just what we did back there. That is wrong. Why is that wrong? Because we found that M was 15, and then the range is 0 to 12. So that can't be the right answer. So actually, and you can probably guess by the fact that we have this problem in existence, it's going to, the tangency point is going to be on this part. So we're going to have to solve the problem the hard way. So it's going to be between so when you're solving this problem, you should recognize that promotion doesn't change our preferences. So what that's saying is that keep in mind that the consumer's preferences are expressed by the MRS, which is the left-hand side of this equation. A over M remains the same. So let's go ahead and take this budget constraint. So we're going to go ahead and advance in the problem. Let's take this budget constraint and simplify it. Actually, we don't need to write that. Yeah, let's go ahead and just jump steps. So I'm just copying what we did before. We wanted to do all this, whatever. All right. Yeah. Sorry, we just simplified that there. Does it get you questions so far?
Where does 0 come from?
Oh, that's a plus sign. It should be that. Yeah.
Oh.
Yeah. I just copied this. It's the same thing. We just simplified it. All right. So let's intuitively think through what's happening with this budget constraint. So we've got a new budget constraint through the promotion. Sorry. Go ahead.
You missing a no, you moved it over.
Sorry. Is that correct?
Yeah.
Okay. All right. So, all right, let's go ahead and look at this budget constraint and break down intuitively what's happening here. So, we rearranged it into a particular form. This is the new price of M. There's a 1 here. That's the new price of A. And we've got a new oct. So this looks just like the form sort of this form here that we used before, except we've got totally different numbers in the prices and the income. So functionally what happens when we get a discount? When we get a discount, two things are happening. First thing is that our price ratio is changing, so our prices have changed. That should be obvious. The second part, less intuitive, but going forward obvious, is that our income is now different. All right, so let's go ahead and solve this problem using that information. So actually, I'll do it over here. So we got the MRS equal to price ratio, same thing. And then we got A over M. So we could do this. So we could do the MRS equal to price ratio. Actually, the recommended solution that you should do is don't even worry about this stuff here. We've got a new budget constraint. That's the only thing that's changed. You're going to take the information from the new budget constraint and plug it into these equations. So actually, let's go ahead and forget about this stuff. So we've got new answers. We've got 24 and 12. Does anybody have any questions for how we got that? So what we did is we just plugged in, we have new prices and new incomes and put it into the same equation. So here's a general tip for what you're going to do when you solve these sort of problems. You're going to want to go ahead and try to keep the problem as long as possible in the form where there's just variables and not numbers. It may seem easier at the beginning to do it with just numbers, to sub out the variables for the constants for numbers. But in practice, if you're looking at the problem in the exam room and there's more than 3 parts, there's probably going to be some variation later in the problem. As long as you have this form here, then you can jump a lot of steps and not do other stuff and just plug in the numbers and then you're all set. All right, so they asked us to double check the, actually they don't ask here. Yeah, so we'll just go ahead and do it, just to confirm to ourselves. So we're going to find the utility at the different points to make sure that we're doing this correctly. So do you guys have any questions? No? Okay. So this is our new allocation. This is clearly bigger than that. So this is the optimal allocation. This is better. This is a better point to be at. Although we already eliminated it earlier. All right, good. All right, so we're going to move on to back to the, I guess the first page of the notes. So you guys flip back to your first page. So we're going to go over the electric vehicle example from class. We probably won't have time to finish it, but these notes follow exactly from class. There's a couple changes we'll make in there, but it's basically the same thing. Let me just go ahead and erase everything here. is exactly the problem from class. Let's go ahead and write down the consumer's utility maximization problem. It's going to look like the following. We're going to solve this problem in 2 stages. So, again, the main point of this problem is to figure out, if people want electric cars or general vehicles. There's 2 stages to this problem. So, you guys have a question?
Just from the budget constraint,
Yep.
did you use less than included here, but not the other time you utilized?
So we did it here because the this problem's kind of confusing. If you keep in mind, there's like a spectrum of consumers between between different ranges. For intents and purposes, it's going to end up being an equal sign, but just in this case, we've done it that way. You don't need to think too much further into it. Actually, go ahead.
What are your variables stand for?
Yeah, sorry. So it should be. Do you have the notes in front of you, or okay? So this is the consumption. See, consumption again. PI is the price of each kind of car. So you have an electric vehicle and a general vehicle, gasoline vehicle. And then CI is the cost per mile. And then M is the miles traveled. And then Y is our income, our total income. Go ahead.
Why are you adding C to the equation? Like, why is it C plus PI plus CIM as opposed to just PI plus CIM?
Yeah, so the idea is that in this particular problem, it's set up such that we don't derive utility from owning the electric car. All we derive utility is by how much money we save, right? So big C here, the thing that we're maximizing on, is in practice the leftover consumption that we have.
Consumption of what? Everything.
Everything else, like life.
Shoes, food,
Yeah.
vacations.
And then essentially, the cost we spend on the car and the cost we spend driving around are unambiguously, they fall out, they're just bad.
Okay.
All right, so there's 2 steps that we're going to solve this problem in. So you're going to do the optimal consumption given the car type. And then consumers will choose the car type I that gives them the highest utility. All right, so let's go ahead and talk about step 1. So in step 1, we're going to find the maximum consumption value given the choice of car type I. And then it's going to be the following. The optimal level of consumption is going to be where we have the following. Essentially, all we're doing is rearranging the budget constraint. We get the following.
So that's the maximum consumption.
That's right. Yep, that's the optimal consumption. So just to break apart what this problem is, the choice that we have is the type of vehicle. So all we're changing actually is not any of these particular, well, we're going to change the numbers, but what we're doing is we're changing I. Once we know what I is, these are all numbers that plug in. All right, so what's the best car type to choose for a given number of miles and travel? So there's a couple parts to step 2. Actually, it's basically the rest of the problem set. So, or the example. So, what's the cost per mile of driving versus a GV? The process for doing this relates to, if you go back to high school chemistry and you remember your chemistry class, you guys did stoichiometry, hopefully. You're basically going to cancel out units. miles times dollars over gallons. So we're just using the numbers that are given in the problem. All right, so we've got the following here. For those of you that have the worksheet, these numbers are literally just written down. All right, so next we've got to figure out what is the utility level from each type of car, and then under what condition will a consumer buy an EV. First, let's address the question of under what condition a consumer will buy an EV. So we're going to need the following to be true. And then I'm going to go ahead and take this information that we have here, written out here, and then start plugging that in here. So we have the following. Plugging in numbers, so plugging in what we found is the cost per mile. This is going to simplify to the following expression. Alright, so what does this simplified expression tell us? I'm going to go ahead and rewrite it in one more form, and then we'll go ahead and talk about what it's telling us. I'm going to rearrange it so it looks like the following. This x here is a new variable that I've introduced. We're going to call this the threshold. So what are these expressions telling us? Consumer will purchase EV over GB if over this threshold. All right, so this next step is a bit confusing, and actually this is probably the last thing, or second to last thing we'll talk about today, is what fraction of consumers will purchase an electric vehicle? So there's a fact that I've left out of the notes here, but it's talked about in the lecture notes, so let's go ahead and write this fact down. So we're given that there's a uniform distribution between 5,000 and 80,000. So how many of you guys have learned about CDF's conditional cumulative distribution functions? Have you guys done this in other classes? Okay, so limited access. So I'll give you guys sort of the general function for CDF.
Is that miles driven?
Yeah, sorry. They're in the lecture. I just forgot to write them down here, but they're in the notes. They're just definitions. Sorry, are there other questions? Sorry, do you guys have a question back there?
I'm just wondering what that consumers will purchase EV over GD, the next word is. Oh, yeah.
Yeah, over the threshold. Yeah. I just made it up. It's a new variable that we're going to introduce here. It's going to become relevant in the next step because we need it when we're setting up the probability function. Go ahead.
What happened to the end?
I just replaced it.
Oh.
Yeah, it's n.
Okay.
Anything else? Okay. All right.
So X is going to be taken from that, and zero. Is X between 5,000 and 80,000?
Yeah, that's right. We're going to go ahead and do it out. All right, so let me just write down some general information on CDFs. All right, so it'll end up looking like this. Uniform distribution. Uniform distribution. Make sure you send that to your friends. Actually, make sure that gets on Instagram, please. All right, then we've got the following. So what we did is we want to figure out basically what proportion of people, when it's uniformly distributed, are going to be accounted for, given a level of X. So X is basically some number between 5,000 and 80,000. Given that number X, what proportion of people are captured? And then finally, we're going to do the demand function. We're going to take this thing, this expression, remember where this comes from, this is what we call the threshold. Taking this threshold, we're going to plug it into where X is going to be. And we have the following. One fact that I left off the sheet here is that in this universe, there's a population of 1 million. Given this, we're just going to multiply that by 1 million, and then we're going to find that the total quantity demanded is the following. Good. All right, guys, we're going to go ahead and stop there. The rest of it follows as in your lecture notes, and otherwise I'll see you guys next week. All right, good luck in your problem set.
Yeah, I have to do my weekly